Right, so what do we mean by wave-particle duality? So earlier on in this course, we've looked at the Young's fringes experiment, where laser light was diffracted and then we had interference. So the Young's fringe experiment is strong evidence for the wave behavior of light, and that is one of the significances of the experiment. Earlier on in this series of videos, we looked at the gold leaf electroscope, which is the photoelectric effect, and we said this was strong evidence for the particle behavior of light. So we've got two distinct models, wave behavior, particle behavior. And normally we assume a lot of particles in physics, for example, electrons, behave as particles because they have a mass, they have a charge, they have a velocity and a position. So we would normally assume that electrons behave as particles. So this takes us into the electron diffraction experiment. So this is a really important thing that you need to be able to describe in the exam. So we've got an electron gun where we produce a beam of electrons. So we don't need to understand this process, but it's due to a heating, something called thermionic emission. So we produce a beam of electrons and they're attracted towards a positive electrode, the anode, and then targeted at a target. So usually carbon or graphene, and then we get this circular pattern. So what's happening is we're getting diffraction, so that's what waves do, and then we're also getting interference. So we've seen this in the waves topic, we're getting constructive and destructive interference. So this is really, really strange because the electrons are behaving as particles at the start and at the end when they interact with the phosphor screen, but in the middle they're behaving as waves because we're getting diffraction and interference. So this strange behavior of particles and waves is called wave-particle duality. So we've seen already that light waves can behave as particles with the photoelectric effect, and the electrons can behave as waves, which is very, very odd. So this is a key aspect of quantum physics. So on a very small scale, we cannot predict with certainty where a particle actually is. And trying to visualize this is very, very difficult. So we could imagine a wave of particles or particulate waves, but neither of those is quite right. It's actually a probability wave. And when we look for the electron, then the probability wave collapses and we have a likelihood that the electron will be in a particular place. It's a very, very counterintuitive idea. So we need to make sense of this and understand which model to use in a particular circumstance. So these are some guidelines here. So if the light is interacting with matter, that is the photoelectric effect, then we use the particle model. If the wavelength of light is similar to the dimensions of the object, we use the wave model, and we saw that in the wave topic. That's when we get the most diffraction. If matter interacts with matter, then it's a particle. Well, that makes sense. That's a transfer of momentum, and that's Newtonian forces. So this final point is really key. If the wavelength of the matter is similar to the dimensions of the object, then we use the wave model. But that begs the question, well, what is the wavelength of a particle? So we need a new formula, and this is the one that we use. This is the de Broglie formula, or the de Broglie formula. And sometimes this is referred to as the wave-particle duality equation because we have the Planck constant, that's the constant of proportionality. We have lambda, the wavelength, which is obviously a wave property. And on the bottom, we have m times v. Mass and velocity, m times v is momentum. So this is combining particle properties and wave properties. So let's have a look at a few examples using the de Broglie formula. So there's a few questions here. If you want to pause the video and try these yourself, that might be a good idea. So this first one we've got, it says find the wavelength of an electron moving at a particular speed. So we know the Planck constant, we're given that, and we know the mass of an electron, we're given these in the formula booklet. So if we put these into the de Broglie formula, we get Planck divided by the momentum, and we get this value here, 7.3 10 to the minus 11. What we need to do then is compare that to the gap that we're passing through. So we've got a wavelength of 7.3 10 to the minus 11. The lattice spacing, that's the gap in this particular case, is 8 10 to the minus 11. But they're both 10 to the minus 11, that's the same order of magnitude. So we would say that we do get diffraction, and therefore in this instance, this beam of electrons is going to behave as a wave. So we could do this for some other examples. So if we have a neutron beam, well, that's the mass of a neutron moving at this speed, same as before, and a slightly different gap. The first thing we do is to calculate the de Broglie wavelength, and we've got Planck constant divided by mv, and this will give us 3.68 10 to the minus 13. So then if we compare that to the gap, 8 10 to the minus 10, so we're a factor of approximately 1,000 out. This is much, much smaller. So this beam of particles is just going to pass straight through the gap. We won't get any diffraction. It won't behave as a wave. It's going to behave as particles. We can also apply this to any situation. So rather than just at a very small or quantum level, we can consider cars and planes and people, and we can work out their de Broglie wavelength. So for example, if we have a person with this mass and this speed here running at a doorway or running through a doorway, a gap of 0.8 meters wide, we can ask the question, do they behave as a wave or a particle? So the first thing we need to do is to calculate the de Broglie wavelength. And not surprisingly, because we have a fairly large mass and velocity, and Planck constant is very, very small, then we get this tiny, tiny wavelength, 10 to the minus 36. So this is so small as to be totally negligible in our day-to-day life. We cannot see this in any way or really measure it, but we can calculate the wavelength. And then we can compare that to the doorway gap of 0.8 meters. So similar to the previous one, there is a wavelength, but it's so tiny that it's not going to have an effect here. So fortunately, people in this case are going to behave as a particle rather than a wave, which is great, because if you diffracted into a room, that would be a little bit socially embarrassing and possibly a bit unhygienic.